Welcome to the continuation of the lesson on finding lines for 2D interference. We'd like to expand what we did before and talk a little bit about finding the locations of constructive and destructive interference for light. So if we have two sources and the two sources are separated in the two-dimensional space in front of the sources, you get these lines of constructive and destructive interference. If you kind of use a little baseline and a center line, something like that, you can start describing, for instance, that you'd have a line of constructive interference along the center line and maybe another line of constructive interference at some angle from that center line. What we did in the previous presentation was to use a little bit of our knowledge of wave interference to figure out how to get an equation for the location of that line. In this case, what we're interested in is this little triangle down at the base close to the sources. If you zoom into that and draw this little triangle here, we found that one side of the triangle, the hypotenuse, was the distance between the sources. Another side that we knew was this delta D. We call it the path length difference. In this case, a path length difference of one full wavelength. And writing an equation for that triangle there with this angle right here gave us the relationship for finding the angular displacement from the center line of any line of constructive or destructive interference for two-dimensional interference. And that was the just quick recap of previous learning that we had. What we'd like now is to kind of zoom out to our big picture again and say that when we're interested in light, when we do an experiment, for instance, where we shine a laser light on two narrow slits, we get an interference pattern, but we see that interference pattern not from above, the way this picture looks, but we see it on a screen. In other words, we place a screen in front of the sources, and we're looking at the pattern that we see. And it looks a little something like this. On the center line, you'll see the constructive interference will be a bright spot, sometimes called a fringe, a bright fringe. And then each of the other locations where you have constructive interference will also be bright. Areas where you have destructive interference, you're going to have dark bands. And you get this pattern of bright and dark fringes that show a pattern associated with constructive and destructive interference. Now, what we're interested in this case is this. We're not interested really in the angle now between the center line and the first line of constructive interference, but we're interested in the distance as measured on the screen. And what we're going to do in this lesson is to just develop really quickly an equation for finding that value x, the distance from center to any constructive or destructive line of interference. Well, you can kind of see here we have a new triangle that we might set up. The base of that triangle is just L, which is the distance length between the sources and your placement of the screen. Completing the triangle, you can kind of see here that we've got our angle that we used in the previous equation, and that allows us to write a fairly simple trig equation, in this case using the tangent. The tangent of that angle will equal x, the distance from the center to any fringe line that we're interested in, divided by the length or distance between the sources and the screen. Now, here's what things gets interesting with the derivation of the equation for light interference. It turns out there's a trig relation that only works for very small angles, but when angles are very small, the tangent of any angle is equal to the sine of any angle. You can probably anticipate that we can use this relationship now to combine these two equations into one relationship for light interference. Looks a little something like this. We said the tangent is equal to x over L, the sine is equal to delta D over D, and so that is our relationship here for the interference in light. Now, most of the time you'll use this equation to solve for x. You'll be interested in how far from the center a line of constructive or destructive interference will be located, where your delta D will be, of course, your different pattern associated with constructive or destructive. So the delta D could be a half of a wavelength or 1.5 wavelength for destructive interference, 1 wavelength, 2 wavelengths for constructive interference. And that's the relationship that you'll use for finding interference of light projected on a screen. Thanks for joining me.